Hi, I'm Alistair, and this is part of a series of videos where I'm going to show how I took apart an old fruit machine and took the electronic components out of it, tried to figure out how they worked and to use them in other ways, normally making them powered by an Arduino. Now, in this video, I want to look at these rather nice chunky LED displays. So these are 7-segment displays, and they were used at the top of the machine to display the amount of money that was about to be paid out to the player of the machine. Now, I've shown something about LED displays in previous videos, and I've shown units like this one. This is a TM1637 powered 4-digit 7 display. And I've got this one as well. This is a MAX 7219 chip which powers 8 7-segment displays. Now the display I'm showing you here actually is in many ways a lot more interesting than those, because this actually isn't a single display at all. These are individual digits which interlock together rather neatly like this. So if you wanted to build a modular display that had an arbitrary number of digits, you can get segments like this. So these are about 1.8 inches high, and they are common cathode digits. So here's the data sheet which I found. I'll put a link to it below as well. So the wiring on the back, what you can see is these grey wires that extend between all the digits here. These are connecting together the anodes of each digit. So let's say this one at the top here, this is for segment A. So this is going to be the segment at the top. That is the anode, so that's where the current is going to be sourced from. And then you've got segment B, C, D, E, F, G, and the decimal point. Then, because they're common cathode displays, what happens? So each segment has its own anode from which current is sourced, but they all sync that current to a common cathode. So that's what's going down these purple wires. So there's a unique purple wire that goes to each digit, and there are these 8 grey wires that go to every digit. And then in order to actually make the display work, what you need to do is you supply a current to the segment that you want to light up. So if you wanted to have the number 1, you'd want segments B and C, for example. So you'd supply a current on the anodes for sections B and C. And then you also ground the cathode of the digit of the display that you want to light up. And by grounding the digits in turn very quickly and sort of cycling through them, that's what's called multiplexing, which allows you to display a number or a value across a whole range of digits. You change them very fast, but because of the persistence of vision that you have in the human eye, you don't really notice that they're actually only one on at a time very quickly. What you can see is a whole number displayed like this. So let me show you how I've got this all wired together on the breadboard, and this is going to look quite chaotic and busy, and there's a lot going on here. So I'll show you the schematic of the circuit in a moment as well. But actually I find it quite useful to see some of the components laid out for real rather than just looking at an abstract drawing. And I'm just going to pull out a few important details just to highlight to you. So I've got my Arduino over this side. Here I have the connector ribbon that's going to my LEDs here. And you'll see that I've got 4 chips on the board as well. And these are actually coming in pairs. So here, this is my high side transistor array. So rather than manually adding a transistor onto each of the 8 pins which I want to drive the anodes, I'm using this chip here, which is a transistor array. So I can apply a low current on one side of the transistor here, and this could be something that was powered from one of the GPIO pins on the Arduino. And on the high side, what it's going to do is it's going to pass, I've got a 12 volt supply here coming down this red lead here. It's going to allow that to flow on the high side through these resistors and into the anodes of the LEDs. That's on the high side. The current then returns through the common cathodes onto this side here, and this here is another transistor array. This is on the low side, so this is a ULN 2803, and that's going to sink the current on the way back. Now, I could power those two drivers directly from pins on the Arduino, but if I did that, I would need there's 7 anodes for the 7 segment displays plus another one for the decimal point, so I'd need 8 pins to drive the 8 anodes on this one, and then I'm using 5 displays, so I'd also need another 5 pins here to decide which of the displays to sync current from. But I'm not doing that. That's what these extra clips here are for. So these are both 74HC595s, and these are shift registers. So what I can do with these, and they're connected together in a daisy chain as well. So using only 3 pins on the Arduino, I've got a clock pin, a latch pin, and a data pin. I'm going to shift in a byte of data, and first I'm going to shift a byte of data onto this chip here. Then I'm going to shift in another byte of data, and that's going to kind of force them to all move down the chain. So by sending only 2 bytes of data on that data line, I can set all of the bits on or off that I want to source current from and send to the anodes. And then I can also set the bits on and off for the LEDs that I want to be able to sync current to. So by doing that, I can actually get away with using only 3 pins to control up to 8 LED digits with 8 segments on each. And here's that same circuit as modelled in Fritzing. So it still looks a bit busy, but hopefully I'll try to explain what's going on. So we've got the LEDs up the top here, anodes, cathodes, our 4 chips, and an Arduino at the bottom here. So first of all, let's have a look at how we source current into the anodes. So I've got these 3 wires here, the blue, yellow, and green, and what happens is so this latch pin here, the green wire, is a latch pin, and while that is being held, we can move data into the shift register on the data line and synchronize with the clock line here. So just using these 3 pins, we can move a byte of data onto this shift register here. Now, obviously, 1 byte is 8 bits, and the 8 bits correspond to the 8 outputs on the shift register at the bottom here. So by moving a single byte of data of 100, 11100 or whatever, those 1s and 0s will activate the output pins here. Those in turn go to the inputs of the current driver here, the UDN 2981. So this chip here is still only running at 5 volts. It only has a very low current output that comes out of here. But the current driver chip here, when it receives that low signal that was sent from the shift register on these sides, we've got a much higher input here. This is a 12 volt input coming in to this pin at the bottom here. And when the pins on the input side are turned on, that's going to allow this higher voltage to flow on the output side. So that comes up here through these resistors here and into the anodes of the LED. Now you'll notice that these resistors are the same for all of the segments except for one at the end. So again, remember the forward voltage across the LEDs is 5.55 volts. I'm supplying 12 volts, and the current across them is 25 milliamps. So using that calculation there, I've calculated that the resistor should be around 260 ohms. You normally always round up. There's never any harm in having a resistor value that's higher than what you need. It will make the LEDs slightly dimmer, but that doesn't really matter, and it's best to be on the safe side. So I'm using 330 ohm resistors on all of the segments, except for the decimal point segment. Because that's smaller, it's got less LEDs in it, so it needs a greater resistor. So I've got a 470 ohm resistor on the end there. So the current flows up through the LEDs, then it back down through the common cathodes at the bottom and into this driver here. So this is the sync driver, the ULN2803. And again, the way that this works is that when a small current is applied on to the input pins on this side, it's going to allow the pins here to be sunk through to ground, which is the connection here. So again, I could have just driven these directly with GPIO pins from the Arduino, but what's really nice about the 595 chips is that they can be daisy chained together. So I've got the output from the clock and the latch lines, which are the yellow and the green ones, are shared between the two chips, and then this is the data line. So this comes out from pin 11 into the first chip, and then there's a serial out on this last pin at the end here, and that goes into the data in of the second shift register. So now by sending 2 bytes, I can send a first byte of data in here, then send a second byte of data in. The first byte will get shifted across. So my first byte of data will control which cathodes get grounded here, and then my second byte of data is going to control which anodes have current sourced to them through this driver chip here. And I say it's actually a little bit simpler. If you look at the schematic view, it's slightly neater. And it looks like that. And here's a quick look through the Arduino code. I'll put a link to this on GitHub in the description anyway, so I'll just talk through it quickly. So first of all, I've just defined a quick macro that's helpful to find the size of an array. That's all that's doing. And then I'm including this separate library here. So that's in the file at the top. And what this is basically like a big lookup table that gives these binary values, so zeros and ones. There's a single byte binary value here for each printable ASCII character. And it corresponds to the segments on a 7-segment display that you want to light up to represent that character. So if we look down here, for example, so a nice simple one is the number 1. So for number 1, and they start with A at this end and go through to G and then the decimal point at this end. So for the number 1 to light up, you want segment A to be off, B and C to be lit, and then all the others to be off. If I then go down and look at something like the letter C, so that's segment A lit, B and C off, and then D, E and F on. So that's how that works, and it's got numbers, letters and symbols as well. Some of them don't print out great on a 7-segment display, but you can certainly get all the numbers and you can get all the letters from A to F and quite a few of the others as well. So that's just what that library is there. Here I'm defining, so I said it only used 3 pins. These are the 3 pins which it uses to connect to the shift registers. So these are wired to the first one, and then the serial out of the first one is wired to the data in of the second one, and the clock and the latch are shared between them. So here's the little function. So I said it was a lookup table. So when you pass in a character that you want to display on the screen, what this does is this returns that series of bits from this table here. Takes away 32 because in an ASCII character table, 32 is actually the first printable character. So the first element here in this array is the space, and that's ASCII character 32. So you just take off 32 for any value you want to look up. Defining an array of char values. This is 5 long because I've got 5 displays. Obviously if you had more or less displays you could adjust that. And to start with, I'm just going to simply display the letters of the word start on each character display. Here I've got a couple of variables just to keep track. If you want to have like a periodically updating display, let's say you want to change it every 3 seconds, so this keeps track of the last time the display was changed, and this is the value for the duration that you want to last in between each change. And then I've just defined a couple of different functions depending on how you want to use the display. So these are really just examples more than anything else. This one here sets a random 5-digit number, so it just loops over each 5 displays and assigns each one a random number. 48 to 58 there, again because the ASCII code table starts at 32, and then you've got to get through all these characters first before the numbers actually start here. So that's where the printable number values are in the ASCII table. Alternatively, you might want to display a random word. So here I've just defined a little list of some example words. I've only put in 3 words there, but you can have as many as you want. They all need to be 5 characters long. So if you've got a word that's shorter than that, just put a space on the end of it like that. And what we're going to do here is we're going to choose a random word from the array, and then we're going to assign each of the letters from that word to the 5 display units here. And finally, this is the final example function. So this is just going to be a counter. So we find out how long the code has been running for with millis. That will give us an answer in milliseconds, so we'll divide by 1,000 to give that as an answer in seconds instead, and that will be how many seconds has elapsed since the code started running. What we'll then do is loop over each display, and we're going to do them from the end back to the beginning, because what we want to do is first of all find out the number of seconds, so the units we'll do by taking the modulo with 10, so that will give us the remainder when we divide by 10. And again, what we do, just this little adjustment here, because we're going from a integer number to a character representation of that number. So we're going to add on 48, so that's the same offset that we were using in this example here. So that's where the character representation of a number starts in the ASCII table. We'll then divide by 10, so having assigned the number of units onto the rightmost LED, we'll then divide by 10 and we'll get the number of tens, then we'll divide by 10 again to get the number of hundreds, etc, etc. So it's just kind of doing like sort of you'd learn to do maths at school, where you kind of calculate the number of units, tens, hundreds, thousands, and you assign them to each one of the LED segments in turn. Setup's really easy. Just we're using all 3 of those pins as outputs. There are no inputs back from the LEDs back into the Arduino, so that's really easy. And then in the loop function, so we'll choose one of those methods depending on what you want to display on the LED. So you can either periodically call set random number, or you can periodically call set random word, or you can just use the counter. So if you uncomment just one of those, and then that will show 3 different modes of operation of the LED. Now all of these functions here don't actually update the LED itself. What they do is they set the value of this value to display array. That's what all of them do. So the thing we actually need to do in the loop function is copy that value to display onto the shift registers, and that's going to source and sync the appropriate pins onto the displays. Unfortunately, that is really, really simple to do. So one more time, we just loop over each of the displays. The first thing we do is we send a low value to the latch pin. So by grounding the latch pin, that's the way of telling the shift registers that we are about to send them some more incoming data. So we hold that low, and while it's being held low, what we do is we first of all we shift out the cathodes, so the displays that we want to display in this frame. And because we're looping over them here, so depending on which order you plug your displays in, whether you plug them in like left to right or right to left, you might just want to count this up, or you might want to count it down. So from 7 minus I, or you might just want I. But in my case, I'm counting down from the maximum to the minimum. And we'll write out that value, just to say that this is the cathode, so this is the segment we're going to display. Then what we're going to do is to say, okay, well, what segments do we want to light up on that display? And we'll do that by sending the next byte of data out to the shift register. So this is what's going to source the current for the anodes. And then once we've done all those updates, so that's updated the two shift registers, they're going to set the appropriate bits which are going to control the current source and the current sink going to the LEDs. Finally, we set the latch pin back to high to say we've done all our updates. And then this is just a little bit of delay. Depending on what refresh rate you want on the LEDs and how long you want between sort of changing them and things like that, you can adjust this a little bit. I found a value of 3 works pretty well, just in between updates, just so that you can hold that value there rather than updating it every single frame. And that's it. So I hope that's helped explain how I got these to work. I think they're pretty nice actually, and if you wanted to create a some sort of electronic project that needed a big LED display, bigger than you can get out of one of these kind of self-contained 4-digit units, for example, then I think these are a pretty good approach to use. So I hope you found that useful, and thanks very much for watching.